This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Recent. What's recent? What's the definition of recent?
That's a good question. Okay. You don't need any of this stuff, do you, John? You're not going to be putting that under. Hi, everyone. I'd like to welcome today our second guest speaker, John Weir. John Weir was an academic, my colleague here at Melbourne University for quite a few years. Then the draw of industry, the draw of consulting was too great. So John then went out and decided to become a consulting engineer using all his design and, to be blunt, the engineering, maths and science that I keep talking about as foundation knowledge, plus the creativity, plus being able to solve problems. And today, John is going to give us, you might think, okay, pressure vessel, I talked to you about it, pretty simple in essence, but by the time John's finished telling you about one of his little projects where he was brought in as a consultant to solve some very tricky problems, you'll be thinking, yeah, you got to take the time, get the team, do the work. So could you please join with me now in welcoming John Weir.
Thanks very much, Colin. It's a pleasure to be here. It is I who should be honouring you, turning up at 9 o'clock on any weekday in Melbourne. I didn't expect to see this many people here, frankly, so thank you for turning up. Can you all hear me?
Not yet. Try again.
Is this thing doing
Yep,
anything?
I had it muted while we were having a chat.
Oh, okay.
Right now? Bit of echo? Yeah.
Great. Okay. I'm going to talk to you about creating a prill tower, and this opening slide just shows us a very ancient tower. Humans have been building towers for various reasons, both religious and military and industrial for an awful long time. This one is the al-Razas Tower in Jordan, built of stone, a very unforgiving material. The prill tower that I'll be talking to you today about is made of something completely different for a very good reason. This project was undertaken as a consultancy with Orica. I worked in that team for about 14 months on the realisation of this tower. But I want to start by talking to you about the purpose of the tower. The purpose of the prill tower is to create prill, or cook up prill. What is it? Well, it's a very important substance used in the mining industry. Orica is Australia's, in fact, I think the world's largest manufacturer of explosives. And ammonium nitrate and fuel oil, when combined, are a very powerful explosive and the most widely used explosive in the mining industry. Mining largely iron ore, but also coal and lots of other things. Prill is a special form of ammonium nitrate, and it's got it's very small. It's got an average diameter of around 1 millimetre, and the size of the pellets is important. But in particular, its surface texture is really important. It's got a sort of frosty, cheesel-like quality to it. And I don't know, if you've ever eaten a cheesel, you'll appreciate how it sort of draws in fluids. And what prill does is draw in the fuel oil into close proximity with the ammonium nitrate and gives it the explosive effectiveness. That's the sort of sizzle on the sausage that Orica use to sell their prill, their ammonium nitrate, ahead of that of other competitors. How do you make prill? Well, you make it from highly concentrated ammonium nitrate solution. In fact, 96% ammonium nitrate, 4% water, and the water has to be driven off. And it's driven off while the ammonium nitrate solution is cooling, and the aim is to crystallise the ammonium nitrate very rapidly and allow it to turn into this little pellet, spherical pellet form. So essentially what you have to do is create a shower of hot ammonium nitrate solution droplets. And to do that, you have to pop it in a shower cubicle with a rose at the top, you know, a container with holes in it that the solution falls out of, and you'll all be very familiar with that. Probably lots of you this morning were in shower cubicles under a shower of droplets. In a prill tower, you have an updraft of air to cool the ammonium nitrate solution as it falls, and it also slows the passage of the drops down under gravity. So really what a prill tower is a big, tall shower cubicle. Now what we see here is quite interesting. I think it's the original designer's sketch. The designer was not me. It was a friend and colleague, Dr. Peter McGowan. Has Peter spoken?
Mr. Peter spoke a few weeks ago.
Okay, so you've met Peter. Very friendly, but occasionally scary guy. And this is his designer's sketch. These are quite rare artefacts in the technological archaeology, I guess, that they're often thrown out or filed away and lost to history, but this is a conceptual sketch that simplifies down the overall process that's going on in the prill tower. I've colour-coded it in three ways. You can see the actual structure in aquamarine. That blue thing is the tower itself. There's a red flow path of ammonium nitrate up in at the top, then as drops falling down and collected on a conveyor belt against, I don't know if you can see the green, but there's a green flow path contrary to the ammonium nitrate of air passing upwards, and it's being received in a plenum at the top of the prill tower, and the air in this case is recirculated. This is a design of a recirculating prill tower. They don't always recirculate the air. If they don't, you get waste air at the top that's full of ammonium nitrate, and the countryside for kilometres down the road is heavily, what's the word? What do farmers do to them? It's fertilised. Ammonium nitrate is not only a great component for explosives, but it's a terrific fertiliser. So on old-style prill towers that don't recirculate the air, you get a lot of very fertile countryside downwind. There's the designer's sketch. Now, prill towers have been used they're the standard way of making ammonium nitrate for explosives use. They've been built, constructed for a long time. Here are some, you can see, made in steel, made in concrete. They're all very large. They all contain the two main components, which is a shower cubicle and some passage or pipe for the flow of air to be provided. They also all have means for access for humans to get to the top of the tower. I'll explain a bit about that towards the end of the talk. They're all, in general, all these historical examples of prill towers have been built in situ. They've been what's called stick-built. You carry all the sticks of steel in, or you pipe the concrete in, and you build them gradually in place. So the creative question was asked, what if we were to build this new prill tower for Orica off-site, to use modular construction, build the whole thing in a factory somewhere and bring it to site and in a very short period of time stand it up. The hope is that being built in a factory, it would be cheaper to fabricate, it would be faster to erect, so it's more economical to construct the prill tower. You have less time on site with large numbers of people. The drivers for those two decisions are economic. You want the overall cost of the project to be less, but it's anticipated that there are going to be some transport challenges. Instead of bringing a whole lot of sticks in and sort of gluing them together on site, you are bringing in this massive structure that needs to be transported to site and stood up on its end. Well, Orica decided to pursue this idea and construct a modular prill tower for their existing ammonium nitrate factory in Newcastle, Kooragang Island, just out of Newcastle. That's an existing site, but it was being very greatly extended. Really in response to Australia's boom time discovery of how important mining was to the Australian economy. And that mining boom is still continuing, although this expansion was constructed during the time when there was a whole lot of new demand for more and more explosives to get the iron ore out of the ground. The prill tower that we're designing, the major dimensions are that it's 70 metres high and 6 metres in diameter. Modular construction, as I've described, and it was to be built from stainless steel, entirely built from stainless steel, 304L, L for low carbon. That's a very important issue to prevent stress corrosion cracking of the prill tower. But the 304 is essentially 18.8, 18% chromium, 8% nickel. So very expensive material to be building such a big beast from. It took a lot of resources, a lot of material resources to build this prill tower. It turns out that the vessel weighs 280 tonnes, and if you do the sums, multiply that by 18% and 8%, you calculate that you require 50 tonnes of pure chromium. I don't know if you could imagine a big sort of cube of pure chromium weighing 50 tonnes. It's a lot of precious metal. And even more expensive, actually, is the 20 tonnes of pure nickel that are required. The vessel overall cost about $3.1 million to buy. A lot of that was straight up material cost, buying all that chromium, all that nickel and all that steel. And when it was delivered finally and erected, the vessel, that part of the project amounted to about $5 million. The modularity was taken to great extremes. The vessel was to be delivered fully fitted with piping, control systems, electrical wiring, the works, a little elevator, everything. Now I want you to think about this prill tower from a structural point of view. I want you to get a bit of a feel for it and for the structural integrity challenges that it posed to the design team. Firstly, let's think about the wall of this structure. It's essentially a pressure vessel, a great big cylindrical vessel, and it's got it's large diameter, 6 metres. To save on all those costly resources, it was constructed with as thin a wall thickness that we could get away with. And after long calculations, it was decided that 10mm wall thickness was about as good as we could successfully and safely achieve. Now, that leads to a diameter on thickness ratio of 600. That is remarkable. That is a very thin-walled pressure vessel. A Coke can, by comparison, has a diameter to thickness ratio, D on T, of 300. And it's a pretty sort of fragile structure, certainly under external loading like I'm imposing on it now. In resisting internal pressure, it's very strong. You can pump these things up and shake them up when they're sealed at the top, and they can take a lot of internal pressure. But if they're subject to external pressure or bending or crushing, crumpling, they're pretty fragile. Well, the prill tower is a whole lot more fragile than that in terms of its wall thickness. But obviously, the prill tower doesn't look like a Coke can. The prill tower is a jolly long thing. It's got a height on diameter ratio of almost 12, compared with Coke can, which has got a height on diameter ratio of about 1.8 for its cylindrical section. So just imagine that, this big, tall cylinder made out of really crinkly stuff, sort of almost made out of aluminium foil. It's, if you could imagine it on that scale, it's really delicate. So what we're faced with is the challenge of designing a very delicate 280-tonne behemoth. I want to take you through some of the ancillary challenges involved in realising, bringing into reality this design. The process of transporting the vessel to site from its factory in Indonesia, and lifting it, erecting it in place, that process had to be thought through in very great detail. And what you can see here is a couple of drawings. There's a long sequence of drawings that we can put together, thinking through every stage of that process and the structural and logistical challenges that were posed. Here you can see the prill tower sitting on a couple of, just look like sort of fuzzy lines here. They're actually massive roller skates with a very large number of axles. So it's 16 or 24 axles on these huge rollers, one at each end under each of the two supports. The vessel that it's being loaded onto has to be weighted to take on ballast to bring it down to the level of the wharf, and when it's at the right level, the prill tower is rolled on, sitting on the ship. And then there's a sea journey. I'll say a little bit more about the sea journey. It gets offloaded in Australia somewhere near the site, and still on its roller skates, rolls off and gets stored for some time in this sort of notional hangar big enough to take it. The skates are removed and it's stored until construction day, when it's brought back onto site. And now we have to think through the process of getting something that's, for transport purposes, has to be horizontal, but for operational purposes it needs to be vertical. So you've got to rotate the thing through 90 degrees. Simple, you might think, okay, that's not so simple really when you get down to the detail. It involved a two-crane lift, two coordinated cranes that were lifting the vessel off its supports. And you can imagine that's a very sort of tricky exercise. The two cranes have to be, they're operated by different people. They have to be coordinated together to lift and transport the prill tower horizontally over some distance. I don't know what it would be, maybe a couple of 100 metres to the point at which it's going to be stood up. The tail end of the prill tower is being stabilised by a series of winches that are helping to move it forward and control it. You can see those in the plan view up here. And as it approaches, in this drawing you can see a couple of set-down pads. Two of them we need, and there's a reason for that. These two cranes, while the ground winches are stabilising the base of the prill tower, these two cranes are lowering and raising the prill tower so it's rotated. The forces in these cables changing as the orientation of the prill tower alters through its rotation. Just before I move on to the next slide, you'll see that the cables are attached at the top and at the bottom. Those attachment points, huge amount of thought and effort went into the design of those. The top one happens to be integral with the prill tower. It's an attachment point that's built into the prill tower and stays there permanently. The one at the bottom end was a detachable lug, lifting lug if you like, that caused us quite a lot of challenge and creative effort. You got to make sure that the cables don't interfere with the tower as it rotates around. And eventually it gets near to the vertical. But because we've got this detachable lifting lug on the bottom, we have to take that off. So there's actually a two-stage set-down process where the prill tower is dropped down onto, in this case, the right-hand pad, and the lifting lug is being. This crane is now detached. The base winch is the only thing stopping the prill tower from swinging like the clapper on a great big bell and sort of bringing the whole structure down. It's all very carefully stabilised until it's sat down on this temporary pad. The base lug is lifted off, then the prill tower is just lifted up by this huge single crane. This is actually a very large and expensive crane. It's then transferred off onto its final resting point and set down in position. So, look, I've probably spent too long on that, but we just went bananas trying to make sure every I was dotted and every T crossed for the construction sequence of the prill tower. It would be a very embarrassing day if you got the thing to site and for some reason you just couldn't achieve the economic benefit of a quick construction process, or, you know, heaven forbid, if there was something that hadn't been thought through and the prill tower would come crashing to the ground. Which brings me to the sort of thought processes that engineers go through when they are trying to achieve a successful outcome. We really do need to think through the process fairly negatively, thinking what could go wrong? What are the various ways in which this engineering objective could fail? So we go through this visions of failure process. I'm fully enthusiastic about the fact that engineers need to consider all of the failure options in order to achieve success. We anticipate failure in all its possible manifestations, so we need to be sort of creative and exhaustive in considering everything that could possibly go wrong. And then we need to identify what's the most serious of those possible modes of failure, and we take steps to avoid that. We're probably designing against several modes of failure, but in particular the governing mode of failure. So what are the critical modes of failure for a prill tower? Well, firstly, if the wind gets too strong, we've got this big tower that's standing in the wind, and it's the major forces on it at that point in time are wind forces, and it's being bent over like a flagpole or like a wind turbine tower. These pictures are taken from the wind industry. And our experience in the wind industry has been bitter. It's known that these things can fail when the wind conditions get too strong. So you really want to avoid this oh shit moment where this beautiful structure that you've given birth to just sort of cracks and falls to the ground. The prill tower was designed for cyclonic conditions, wind speeds of greater than 160 kilometres per hour, to avoid that mode of failure. Secondly, getting it there, it would be really serious if the prill tower fell off the ship while it was being transported from Indonesia to Australia. So you've got to consider what are the most serious but realistically likely sea conditions that the structure will have to withstand when it's lying horizontally in its cradles on the ship. And it turns out there's a great deal of literature on this. It does depend on the time of year and the sea route that you take. But if you don't want to constrain the time of year or the sea route, there are worst case sea-going conditions that you can design for. And it turns out that they're actually dynamic loads. The sea is the waves are causing the ship to rock around, pitch forward or roll sideways. It doesn't roll to 63 degrees or pitch to 60 degrees, but these are the statically equivalent configurations that give rise to the same dynamic forces that you have to design against for these sea conditions. So imagine a ship that, if it was just sitting there at 63 degrees of roll, that's the amount of force that the prill tower has to be able to withstand to successfully navigate those sorts of sea conditions. Or a ship that's pitched 60 degrees forward, that's the static equivalent of the dynamic pitching into the waves that you have to cope with. And really, these impose forces between the saddles, these are called saddles, these cradle things, and the vessel. So that's what has to be designed for. Failure mode 3 is a very interesting one structurally. We're talking about a pressure vessel here, and the prill tower was designed as a pressure vessel to cope with very small pressures, plus or minus 10 kilopascals, so 1/10 of an atmosphere. But it's the minus 10 kPa that causes the real challenge. That external pressure that puts the vessel in, puts the vessel's shell in compression. You can picture that. Normally, if we've got an internally pressurised vessel, the vessel's shell is in tension. It's actually quite an efficient way of containing fluids under internal pressure. But under external pressure, there's all these problems associated with thin-walled pressure vessels. And the mode of fuckling, the mode of failure, the mode of fuckling is buckling. The mode of failure is buckling under external pressure. So the shell is in compression, and they actually fail in these beautiful, mathematically interesting ways. You can see here, this is not a prill tower, it's just a grain storage silo, but someone's left a valve closed while opening a fluid, allowing the fluid to fall out, and so the vessel's being sucked inwards under external, probably full atmospheric pressure here. And you get these nodes of, these buckling nodes that are so characteristic of compressive failure of shells. So, local shell buckling under external pressure, uniform external pressure. But as you know, I think, as you know by now, vessels can be subject to compressive stresses in their shells, not just due to fluid pressure, but due to bending. And so the fourth and fifth failure modes that we're designing in the pressure vessel, the prill tower for, are for local shell buckling when the shell is placed in compression due to bending. Now, who can tell me, and this is a hands up moment, who can tell me where the worst case location on the shell of this prill tower is in terms of compressive stresses in the shell due to bending? Got a little bending moment diagram here. It's actually during the construction lift. It's being lifted at the head and the tail, or the foot of the prill tower. It's being lifted from both ends. It's essentially more or less uniformly a beam with a uniformly distributed load. So it's got supports at each end. There's a uniform load across the middle. You've got this parabolic bending moment diagram. We know what the maximum bending moment is. Where on the vessel's shell is the most severe compressive stress? Anyone? I'll spoil your fun in a second. Top surface. That's right. Up. See if I can point to it. Just here, on the top edge of the shell. The bottom edge of the shell is in tension. It's a beam in bending. Top edge is in compression. So there's this little region, it's quite a large region, around the top of the cylindrical shell of the vessel that's in axial compression. So it could potentially fail by that local shell buckling in just the same way as we saw in the previous slide due to external pressure. There's another situation when the shell is in bending like that, and it's when it's sitting on the ship in these rough seas. Very similar situation. It's a uniformly distributed load on a beam in bending, except this time the supports have moved in. It's the vertical reactions are at the locations of the two cradles. We've got a different bending moment diagram, but there's a different set of loads. These are dynamic loads rather than just the gravitational loads of the prill tower's weight. So these are the five main modes of failure that we had to consider. We had to look at all of them to find out which was the most seriously threatening of the prill tower's structural integrity. What's the designer's overall task? Well, the big picture is we want to keep the prill tower as light as possible. We want to keep that wall thickness as thin as possible. We want to avoid all of these modes of failure, and we want to design the prill tower so that it'll conform to the governing pressure vessel design code AS 1210. Now, it turns out that the governing mode, the most serious mode, is the fifth one, that the failure mode of local shell buckling that arises due to axial compression of the shell during sea transport. But all of them needed to be considered. Now, local buckling of cylindrical shells is actually quite a technical topic. There have been international conferences held on the mathematics of that problem. It turns out to be described by a seriously challenging differential equation, 8th order differential equation, but here. But fortunately, we don't have to worry about any of that. The solutions to this problem are available because we're designing the prill tower to a national standard, the Australian standard AS 1210, and there's whole sections in that code that relate to local shell buckling. So we don't need to solve the mathematical problem, it's been done for us. In that general solution, both external pressure and shell bending are covered, and also shells that are not simple uniform shells, but they have localised stiffening rings, and it turns out that we needed to use those for the prill tower as well, to stiffen up this crinkly shell with a series of little bands around it to reinforce it. Better speed up, I think. I just want to say something in passing about the design tools that were used during the design of the prill tower. The preliminary design, done by Peter McGowan, was just done on a calculator. The initial detailed design was done entirely with spreadsheets. It was just a calculation effort in Excel, essentially. You might think that other more sort of sophisticated tools would be needed in a situation like this. It turns out not. Although FEA was performed, finite element analysis was performed, really at the end when the whole thing had been designed, all the thicknesses had been assigned, the design was essentially complete. Finite element analysis was used as a check, and helpfully, because some of these stiffening rings were relocated, or I think an increased number of stiffening rings was included to improve the factors of safety as was necessary. It might also disappoint you to learn that the prill tower was designed entirely using two-dimensional drawings. I guess that would still be the case. It was only a few years ago when this was done. Conventional 2D drawings were used for the bulk of the design process and for the communication with the fabricators in Indonesia. A little bit of 3D modelling was used for a few features just at the end, and I'll go into that. You saw that earlier picture of the Kuragang Island factory. The overall factory was rendered, designed in 3 dimensions using 3D modelling software because a chemical plant is a very complex spatial entity, and all the pipes and vessels and bits of hardware need to be located very carefully with regard to each other. It's incredibly complex. The prill tower, on the other hand, is in general a relatively simple three-dimensional entity. But we did find a little bit of 3D modelling useful just at the end. I want to tell you about this tailing frame design. I mentioned it earlier. This is where you've got the prill tower. It's being lifted by its head, but the tailing, at the tail end of the prill tower has to be attached to this tailing crane. And that's something that needs to be detached later. Well, initially, people thought, we'll put a plate of steel on that and that'll be fine. You know, it's just a lug, it's just a lifting lug. They thought, well, let's just for argument's sake, we'll make a 50 mil thick steel plate. It weighed 7 tonnes, and it was seriously inadequate. Once you start lifting it using just a flat sheet of steel, you end up with something really heavy that still fails. It still bends under the forces that the bending forces that arise as the prill tower rotates around. So we came up with this different design, weighed a lot less and was structurally okay. It did the job. We were able to ensure that the bending stresses in this were going to be fine. We needed to do a little bit of, I don't know, second year, first year force analysis, second year force analysis to work out what the forces are in the cables. I mean, the force on this lifting lug here is the force Q from the tailing crane cable, and the force Q and the head cable tension P. They're both solvable in terms of the angle of orientation of the prill tower and the weight of the prill tower passing through the centre of gravity here. So we can calculate all those forces, therefore we know the geometry of the lifting lug, we can work out what the bending stresses are. That's the sort of exercise I reckon any one of you could carry out if you had enough time and confidence, but you should have the know-how to do that already. Those changing forces as the prill tower rotates through from 0 degrees up to 90 degrees, you can see how the head cable force goes right up to the full weight of the prill tower. The tailing cable goes right down to 0. Once it's vertical, there's no force in the tailing cable. You can convert those forces into bending moments, and there's an angle of rotation which is the worst case in terms of stresses on the tailing lug. So really what we're using here is just a little bit of maths and physics and spreadsheets. These are the designer's friends, and I hope you sort of feel like they're your friends too. That's how you would get through a challenge like working out how to design this tailing lug. But it turns out that if you use that simple tailing lug that I showed you on a previous slide and grab the prill tower shell, this thin shell from the top and the bottom, and lift it from there, you get some serious distortion of the shell that actually leads to very unhelpful bending stresses in the shell. You're lifting it from a very inefficient location because the shell of the prill tower up there and down there, those two, can you all see the pointer waving around there? Those distributed forces are really where the shell is very weak in terms of being able to transmit forces in a vertical direction. It's much stronger on the sides where the shell is basically vertical. So we, in the end, designed a different lifting lug that lifted the prill tower shell from the sides, not from the top and bottom, but from the sides, here and here. The lifting lug is only attached to the prill tower on these 6 bolts over here and these 6 bolts over here. Why did we do that? Well, I've sort of explained in terms of the stresses on the shell of the prill tower. And this was even lighter. We could get an even lighter lifting lug because ultimately the weight of the lifting lug is yet another thing that this huge crane that ends up carrying the whole weight of the prill tower has to be able to support. So you really want the overall lift weight to be minimised. I think we got up to something like 320 tonnes with all the other bits and pieces added. I want to talk briefly about the transport saddles. Remember, these are the things that support the prill tower during its most crucial, the most serious critical failure mode, when it's on the ship pitching around in rough sea conditions. And right at the end, finite element analysis revealed that we were inflicting some quite serious bending stresses on the shell of the prill tower in this little region near the tip. They're called the horns of the saddle. There's all this sort of jargon that the pressure vessel industry uses. In that region, and this is a purely standard orthodox design of a saddle. And often if you've got a horizontal a vessel for storing petroleum or whatever, it'll sit in standard saddles that look just like that. But these are just being, for the prill tower, these are just being used for transport. Well, something needed to be done. This was not acceptable. We were going to end up bending the shell of the prill tower beyond its elastic limit. We'd end up with little dents in it, and that's really, really bad. You don't want that. So we looked at a number of other alternatives. This is alternative C and D. There were various ones that we looked at. I won't go into them all, but with this one, this is the one we actually adopted, was to modify the standard saddle by turning it into a full ring saddle, and it really provides a passionate embrace of the prill tower around its full perimeter and prevents it from distorting in the ways that led to the bending failures that we were concerned about. Another way to do it would have been to build like a space frame and support it at a number of points around its perimeter. Well, as I said, we went with the full ring saddle designs. We had to incorporate some serious props to resist the axial forces that occur when in the pitching motion of the ship when it's sort of diving in headfirst into the waves. This 280-tonne prill tower is wanting to leap off the front of the ship. You've got to resist that. So we incorporated these props and did the calculations to make sure that they were adequate. Okay, finally, I just want to say something about the role of human factors design. The prill tower is not just a shower cubicle for ammonium nitrate. It's actually a work environment for a couple of humans, fairly unfortunate humans, I would say, but it's not a very nice place to work. But people do need to work in this area at the top of the prill tower called the head house. Intermittently, about once a day or once every couple of days, two people need to go up to the head house where there's lots of equipment and they need to work there. They need to do a changeover of a vital piece of the hardware of the prill tower. It's a difficult space to work in. It's very compact. It's full of pipes and equipment. There's not a lot of space to move around. And it's spatially challenging. It posed a three-dimensional design problem to us. So this is where we did actually use a bit of 3D modelling. This is the external view of the head house. I'll just sort of do a bit of a reveal here. If we take away the shell at the lower floor, there are two floors in the head house. You can see there's lots of equipment in there. There's lots of equipment in the upper floor as well, but the workers actually do their work in this lower floor. They take a lift up. There's stairs up, but they will generally take the lift. There's this beautiful spiral staircase. I could tell you about that too. That actually involved quite a lot of conflict and negotiation between the designers and the fabricators about how much the spiral staircase cost, but that's another story. Anyway, in here there's a thing called a prill head. Now, I don't know if you can see the prill head between these two. I've just removed a little bit of electrical cabinetry there, revealing the prill head. The prill head is the shower rose, if you like. And over a couple of days, it sort of glugs up with, as you get some crystallised ammonium nitrate plugging up the holes. There's thousands of holes in this shower head. It's about that big. And its effectiveness deteriorates. Some of those holes stop working. So the prill head needs to be changed over. There's the prill head there. Let's take a close-up view of it. There are two prill heads, one that's in use and one that's about to be in use. This green thing here is really just the swept space that in our design, in our new design, the prill heads swing through as they get moved into place. But it's this red thing that we're trying to manoeuvre. And the prill tower has this single prill head in operation at any time. It's located centrally on the tower. It has to be on the centre of the tower, geometrically. It gets clogged, as I've said. The changeover process is on the critical path. It has to happen quickly. You don't shut down the plant while you're changing over the prill heads. It's churning away, producing so many tonnes per hour of ammonium nitrate. That gets stored in a temporary tank, which gradually fills up while these two workers are beavering away, changing over the prill head. If it's too slow or something goes wrong, the tank overflows and you just get ammonium nitrate sort of frothing down the side of the tank. It's very sort of spectacular and dangerous because it's really hot. So we've got a challenge for these human operators. The changeover task is manual. They have tried automated prill head changeovers, but that leads to other problems to do with complexity of the hardware. It needs to be safe, we can't compromise the space, and it has to happen quickly. So our solution was to come up with a simple mechanical solution involving swing davits. And we designed this up, and it needed to be talked through with the operators. There's sort of industrial relations issues related to every aspect of the plant, and the operators needed to be sure that this change to the way they were going about their work was going to be good for them, safe for them, and wasn't going to do anyone out of a job. And anyway, they became enthusiastic about this design, which can be set up while it's online. It's a short offline time, very little, no direct lifting, and the operators were on board. So it just sort of goes like this. How about that? It's such an obvious design, really. Just swing the old one out, put the new one in, and then there's a bit of bolting up and plugging in, and the operators still have to do their work, but it's a design that was driven entirely by concern for the human operator. Okay, well, the design of the prill tower was a really challenging and satisfying project to work on. There were lots of problems that had to be solved, problems at a conceptual design level involving technical analysis, lots of maths and calculations, management of cost, and project management issues to do with the construction phase. Designer needed to consider lots of different issues, process requirements, the flows of prill and air, structural integrity of the prill tower, human factors, ability to manufacture this thing and construct it, transport issues too. So I've said that it really involved bold design, meticulous execution, and we needed to sweat the details. And sort of using an anally retentive person like myself was probably a good move, because you've got to think about the problem in very great detail. There's a picture of anyone have a guess at what that tower is? Tower of Babel, yeah, that one really didn't end up well. But the prill tower for Orica did end up well. Here it is on the day when it was rolled out. It was sort of gift wrapped in black and blue plastic. All the bits that I was really heavily involved in are in yellow for some reason. The saddles, the lifting lug, the spiral staircase, all that sort of stuff. Another view of it. It's the load-out day. There's something special about seeing the arrival of a structure that you've been involved in from the point at which it was a twinkle in your eye. You know, you sort of thought things out. It was a sketch on paper, and it turns into a bit of engineering reality. That's very satisfying. There it is. On the barge, you get a great view of those roller skates. I don't know, I can't add it up, but I think it's a 16-axle roller skate, front and back. Okay, I think we've got a couple of minutes. Not long for questions, but I'll...
Thank you very much, John. Is there a question?
Is there an estimate on how much cheaper it was to manufacture this?
Look, yes, there were, and the decision to use modular construction was taken on grounds of economics. Actually, Peter McGowan would have been able to tell you that. I think it was quite seriously cheaper, like it was a couple of $1 million that was saved by doing it this way, even with the additional challenges that had to be overcome in transport. Yeah.
It's fair to say, John, that your cost, the cost of the engineer, was
nothing. Nothing. Peanuts.
It's that, it's that you do all the thinking up front. Yeah. It's an awful lot less than buying all that material.
Yeah. Design on paper is always better than design in steel. The engineering effort was absolutely worth it. Was a very small proportion of the savings. Yeah.
You had a question?
Does it have to be made in one part, like separated?
Look, they did consider making it in two parts and bolting the two together, and that just added complexity. When you have a permanent joint that you've created, that means that there are huge issues to do with tolerancing and the construction process. So you can imagine a bottom half, and then you have to lift the top half onto it, and it just turned out to be not worth it. No, I think they quickly discounted that idea.
Well, everyone, it's 3 minutes to. You've probably got another lecture to go to. Thanks again to John for being here. Thanks to all of you for coming as well. I'll see you next time.
Yeah, they should all get bonus points.
You might not know, John, but I do actually ask the odd exam question about your presentation.
Which one have we asked this year?
Well, a few interesting ones. I was thinking about, I can show you, I've put it in red. If I can follow this. Oh, sorry, I'll introduce you.
Hi.
John, this is Saeed.
Hi, Saeed.
Good to meet you.
So he's doing a PhD?
Yeah.
With Colin.
Yes.
Yeah. I'll just quickly finish this off. Why build off the stick build?
Yes.
Yeah, just that. The L. Why would you have L? Yeah, what you said.
Right. Oh, that was a throwaway.
Yeah, I know.
That'd be nice.
What mode of failure does the Donald equation assist with?
Yes.
And then maybe cut and paste that chart, that graph, and say which is which cable.
Yes.
Cut everything else out.
That'd be good.
They're the kind of, and I was thinking about what are these things? What are they for? I was thinking about that as well. But that's my least favorite one. You had a question for Ty?
Yeah, about the crane, the primary crane.
Yes.
Was that custom built, or was it difficult to find a 300 ton?
It was very difficult and expensive.
Excuse me, John. If you guys could just have...
Yeah,
you just go. I'll grab it. You guys keep talking. Our next lecture is just about to start. So I'll just tile this off for you.
We are going back to your office.
Oh, we'll just come outside.
Yeah, that's right. It's not
Just out of it, what's the picture depicting?
That's a prill tower.
Sorry,
A prill tower. It's essentially for ammonium nitrate, for anthode, for explosives. And you have these little crystals, they flow down. And then in that process they get turned into a little ball that then fits nicely against the fuel.
It's a shot tower for explosives.
You got it. Yeah.
So
sorry about that. Quit. Do we have to restart to get you in?
Just log out.
It is.
Yeah, okay, I'm good.